All right, profiling part 2. I'm going to do a little bit of a demo. I'm going to show how to profile with the tools you've got in our C++ code. What I'd like to do now is show you a little bit of the sampling profiler that is built right into Visual Studio. We use Visual Studio for our labs, so if you want to get a quick and dirty sampling profile of your lab to say, hey, why is it running slow? This is a great place to start. During this week's lab, we will be specifically putting in an instrumented profile approach that you will, of course, also want to use. But this is something that you always have available. So here I have written a little program, very small little program. It's just going to start at 1 million and then ask, is the number prime? If it is prime, print it out and then advance to the next number. Of course, million is not prime, but I think maybe 1,000,001 is. I don't know. Who knows? We'll find out, right? So let's just run it and take a look. It just prints out all these are prime numbers and just print them out, and it never stops. You have to kill it to make it stop. Okay. Let's show that same thing in the performance analyzer. So go to the debug performance profiler, click that, and that'll open up this little dialog box with some options. We just are going to want to use the CPU usage option. So we'll start. When we start it, Visual Studio launches your program, and it is doing this sampling profile. I'll try and stop it right about 2 million. There we go. That was pretty close. And boom. Visual Studio collects all this data. It was doing samples that whole time. Apparently, while we were running, it took about 4,300 samples during that period of time. And of the time, we can see the vast majority of it was inside main. That should come as no surprise. There was a little bit of startup that took place before main, and then all the rest of the samples were in main. Duh. Okay, so one of the things I really like about this is you can click on these and it'll take you there in the code. So let's take a look at main. Here's main right here, and this is our main function. And not only does it show you the code, but it shows you a heat map of where the time was recorded, how many samples landed there. What we see here is that 85% of the time was in this is it prime function. And honestly, that shouldn't be a surprise either. That's really all we're doing here. So let's go back to that and let's take a look at the is it prime function. Do the same thing. We'll look at that heat map for the is it prime function, and we'll see the hotness is this line here. 74% of the time is in this square root line. So now that we know where the program is slow, the question is, what can we do about it? How can we speed this up? So now that we've done our profiling and we know where the slow things are, how do we optimize it? Often we can look for an algorithmic solution. This is the kind of thing you've learned in your regular CS classes. Like, for example, if you're currently using some kind of algorithm that's order n squared, maybe there's a faster algorithm, an algorithm with a faster big O, right? That's the go-to often. Probably not going to get that much mileage out of that, honestly, because you're smart and you probably already went with the better algorithm to begin with. If you didn't, hey, great, do that now. How about this one? Just reduce the frequency with which you call that thing. Maybe you don't need, this is I always say, the fastest function is the function you don't call. So before you call the function, before you go through the process, ask yourself, can I early out? Can I skip it? Like, maybe ray casting is a bottleneck in your game. So we could try to make ray casting faster, or we could just try to ray cast less. For example, why are we ray casting so much? Is the enemy trying to find the player? Maybe the enemy has a maximum range. check the maximum range first before doing the raycast. Maybe there are other things. Maybe we can turn off groups of enemies in a big block. Turn them off, and then only the on ones, the only ones that are turned on, will do this raycast that's expensive. Maybe we can do something like that. And then, of course, we have all these low-level optimizations, and that's the ones we've been talking about in this class. Things about taking cache into consideration and designing things in that way. So we discovered that the isItPrime function is slow, and more specifically, we found that this line 13, with the square root in it, is the slow line of code. What can we do about that? Well, without even really understanding why it's there, we can approach this simply from a code structure question. We can see that the number is being cast to a float. That is being square rooted with a square root call, cast back and put into a local variable. All right. And that is done inside this loop, and then some more stuff is done. We test based on that, and then we use the number for another test. But notice, we do not modify number anywhere inside this loop. Number is tested, it's not modified. That means there's no reason for this line of code to be in the loop at all. Let's put it outside the loop and see if that doesn't make a huge impact on the performance. Let's take a look at what we got from that. Save that. I'm going to run again in the performance profiler just like I did before. And again, I'm going to try and stop it around 2 million. There we go. Okay. Now, if you remember the last time, it was about 4,300 samples, I think. This time it was only 1,600 samples. That should tell us right away that we've made a tremendous speed improvement. Doing the same process took many times longer in the old version as opposed to what it did now. And now, when we look at our hot path, we no longer even see isItPrime in that path. If we look up here, we see it. Apparently, it was 17% of the total time, and the square root was only 1.3% of the total time. So that's much smaller than it used to be. Now the big hot one is the print itself. The printf is the big thing. And if we look at the isItPrime, we can see the heat map and the impact that we have had. This function is now a very tiny contribution to the overall compared to what it was before, with that tiny change of just rearranging the code. So what we found was that originally isItPrime was very expensive, and we found this square root was a major contributor to that. We discovered we could reduce the frequency of that call just by taking it outside of the loop. So we moved this out of the loop, and now we can see the square root is a much smaller part of the overall thing. And in fact, now we see that the print is as expensive as the call itself. So we've made major improvements there. All right, that's it for part 2. Let's take a little break. Come back and join us in part 3, the last part of profiling for this week. And I've got a convenient little link down in the description right down there if you want to just jump to that. See you in part 3.